Welcome to this explainer. Okay, we're going to jump right in today because we have an incredible evolutionary journey to talk about. We are moving from the totally familiar world of classical silicon electronics right into the mind-bending reality of topological quantum computing. Seriously, we are standing on the precipice of a complete technological overhaul. We're talking about a shift that's going to change everything from how we design life-saving medicine to how your personal bank account is actually secured. Here is our roadmap for the journey today. We'll start with the walls of silicon, move into the quantum paradigm shift, explore the decoherence crisis and the topological revolution, before diving right into Microsoft's Majorana 2 and our quantum-driven future.
All right, Section 1, the walls of silicon. Let's start by looking at our classical foundations. So, ever since the transistor was first invented way back in 1947, classical computing has basically relied on one main trick: shrinking. We have relentlessly scaled down our architectures to the point where today we've reached the sub-3 nanometer node era. Just to put that into perspective, the switches inside the chip on your smartphone are now literally just a few atoms wide. It's wild. But here's the massive catch. Classical computing is now trapped. We're hitting hard physical walls. Things like the breakdown of Dennard scaling and the von Neumann bottleneck mean components are getting way too hot, and we're hitting the absolute limits of thermodynamics, which physicists actually called the Boltzmann tyranny. But the absolute biggest wall we're hitting? Quantum tunneling. At those microscopic sub-3 nanometer scales, the barriers between components are so unimaginably thin that electrons just physically leak right across them. The basic physics of silicon simply cannot carry us any farther.
That brings us to Section 2, the quantum paradigm shift. We are quite literally entering a new dimension. The core difference between these two worlds is absolutely fascinating. While our familiar classical bits are totally confined to definite voltage states, meaning they act strictly as a 0 or a 1, just navigating through standard logic gates, qubits play by a completely different set of rules. Qubits leverage complex probability amplitudes. Because of a property called superposition, a qubit can essentially exist as both a 0 and a 1 simultaneously. This unlocks an entirely new, massive dimension of computation.
To really wrap your head around this superposition, it helps to think about the Bloch sphere. In the classical world, a switch is rigid. It can only point straight up to a 1 at the North Pole or straight down to a 0 at the South Pole. But a qubit? It can map information probabilistically anywhere on this entire 3D surface. It's a geometric representation of the qubit's pure state space, and it allows for a level of complex information density that classical bits just can't touch.
And when you look at the underlying math, like Dirac notation, you see how these state vectors map out these probabilities. Through the magic of quantum entanglement, these qubits can instantly influence each other. This is huge because it allows the system to literally cancel out incorrect answers and isolate the absolute truth.
But, the quantum realm is incredibly unforgiving. It imposes some really severe rules. We're dealing with wave function collapse and the no-cloning theorem. Basically, this means you absolutely cannot just back up or copy your quantum information mid-computation like you would on a standard hard drive. The very second you try to read or observe a qubit to copy it, boom, the wave function collapses and that incredibly delicate quantum state is just instantly destroyed.
Which leads us perfectly into Section 3, the decoherence crisis, the sheer fragility of the NISQ era.
So our early attempts to harness these qubits, what we call the NISQ era, mostly relied on two main paths. You had companies like IBM and Google using superconducting transmons to create these artificial atoms, while others like Quantinuum and IonQ used lasers to hold on to actual physical trapped ions. Both are amazing feats of engineering, but they share one fatal flaw. They are incredibly, almost impossibly fragile against any kind of environmental noise.
Because of that environmental noise, those delicate quantum states just completely fall apart in mere fractions of a second. The brutal math of quantum error correction comes into play here, and it demands an unbelievable amount of overhead. You need over 1,000 physical qubits in these architectures to yield just one single, stable, error-corrected logical qubit. It's a total scaling nightmare.
Thankfully, we have Section 4, the topological revolution, escaping that fragility.
Building on the brilliant theoretical physics of Alexei Kireev, we realized we could utilize something called non-abelian anyons, specifically Majorana fermions. Try to imagine a coin that is somehow heads and tails at the exact same time. By harnessing these, we can actually create a hardware-level shield against that decoherence. We're fixing the noise problem in the physical hardware itself rather than trying to patch it up with software later on. And the way it protects this data is just mind-blowing. By splitting a single electron's quantum state across space and physically braiding their paths, the information gets stored non-locally. Because the data isn't just sitting in one single vulnerable spot, it becomes completely protected from the local environmental noise that was destroying those earlier chips. So how does that become real? Section 5, Microsoft's Majorana 2, a massive hardware breakthrough. Discovered with some heavy lifting from scientific AI, Microsoft totally moved away from their earlier attempts with aluminum. Instead, they engineered a highly specific, very complex new material stack. This recipe uses a lead superconductor combined with indium arsenide and indium arsenide antimonide semiconductors. It's this exact, highly specific material alchemy that makes the topological state physically possible in the real world. Then, they took those materials and arranged them into a brilliant H-shape nanowire geometry. And we're talking about an unfathomably small scale here, just 1/100th of a millimeter, which is way thinner than a human hair. This very specific geometry isolates the crucial Majorana zero modes right at the boundaries of the nanowire, practically locking that non-local topological protection into place.
The result of all this material and geometrical engineering? Staggering. Absolutely staggering. Microsoft achieved a 1000x reliability leap. Instead of our qubits falling apart in a fraction of a second, we're now seeing massive coherence lifetimes stretching from 20 seconds to a full minute. This fundamentally solves the decoherence crisis that trapped the entire first generation of quantum computers.
Which brings us to our final stop, Section 6, the quantum-driven future. Looking ahead to the 2030 landscape.
First up, global cybersecurity is going to change forever. A stable quantum computer like this can run Shor's algorithm, which literally threatens to break the RSA 2048 encryption that secures your bank accounts right now. This is going to force a rapid, global shift to an entirely new standard called post-quantum cryptography. Meanwhile, Grover's algorithm is going to fundamentally speed up the most complex database queries we have.
But honestly, beyond just security, we're gaining the unprecedented power to simulate the untouchable. With these topological qubits, we can perfectly simulate chemistry at the quantum level. We are talking about unlocking the Haber-Bosch nitrogenase process, which could give us zero-carbon fertilizers for sustainable global agriculture. It means finally designing true room-temperature superconductors and performing flawless quantum molecular docking that will totally revolutionize cellular biology and drug discovery.
Which leaves us with this final thought to explore together. When these incredibly stable, error-free topological quantum supercomputers are finally integrated directly into our classical data centers in the 2030s, how will your industry adapt when simulating the impossible just becomes our daily reality? It's a profound shift, and one we all really need to be ready for. Thank you so much for joining me on this explainer, and definitely keep your eyes on the quantum frontier.